Hello, dear students. We were discussing about reduction. We were discussing about the reduction of various carbonyl groups by using various reagent. Now we are going to discuss about catalytic hydrogenation. So, if you take if you ask what is reduction, then one of the answer you will be saying addition of hydrogen. So when the hydrogen is getting added, it's as if the electrons are getting added. That's why it is called as reduction. So we can call hydrogen as the simplest reducing agent. And this simplest reducing agent, hydrogen, cannot be added across the carbonyl bond. So what is the reason this carbonyl bond is not nucleophilic enough? Whereas this hydrogen could be added across the weak nucleophile like double bond, triple bond. It could be CC double bond, it could be CN double bond, it could be CC triple bond, it could be CN triple bond, and they are weak electrophiles. And the problem that we come across during the addition of hydrogen, it is the hydrogen will be in the form of molecules. So if you wanted to add this hydrogen across the double bond, you need to break the molecule. How do you break the molecule? You need to have some easy method for breakage of the molecule. That's why we take the help of a metal, especially transition metal. It could be palladium, platinum, sometime it could be nickel, rhodium, ruthenium, etc. And you must have noted that this type of hydrogenation in presence of a metal catalyst is what we call catalytic hydrogenation. So if you take an example, that is an alkenol, cyclohexenol is getting hydrogenated in presence of palladium catalyst to give cyclohexenol, not a hexenol. And what is to be noted over here, if you ask, there is no change for the CHO group, only the double bond has got reduced. Now, this chemoselectivity must be noted, and it is chemoselective towards the double bond, not for carbonyl group. And many transition metals could be used for the purpose of this reduction. And what is common in all this, it is the mechanism, what is going to happen, it is similar, it is same. And one difficulty I have already told you, that the breakage of the bond between two atom of hydrogen molecule, that require huge amount of energy, and this huge amount of energy could be surmounted, or we could bear it if you add a catalyst. So it's a catalyst for the gaseous reaction. So the gases must be absorbed on the surface of the catalyst, and the surface area is very important. In order to have more surface area, you need to make the transition metal in the form of powder, and when it is in the form of powder, it must be supported with it must be having some support. So it will be dispersed on the surface of some inert support. That's why it is written palladium bar C. This C is nothing but charcoal. So if you look at the mechanism, initially you will have the metal catalyst and the hydrogen will be adsorbed, and once the hydrogen is getting adsorbed, what will happen is the bond between the hydrogen atom will get weakened, and the same time will also supply the substance which need to get reduced. So we have taken the alkenol. So what happens is, once you have taken the transition metal powder and you have supplied hydrogen, the hydrogen could be supplied by either by cylinder or by balloon, or it could be made by the electrolysis and pumped into the reaction mixture, and the other substance also will be there, the other substance something like alkene. So the alkene also will get coordinated to the metallic surface, and there the reaction happens. When all this hydrogen and the alkene are together on the surface of the metal, the reaction happens with an energy that is far far lesser than expected. That's what the importance of this metal catalyst. And what happens is, there will be the breakage or the breakage of the bond between the substance which need to be reduced. So what happens, the product will be produced. So here initially there will be this is how it will be. So this is the metal surface, and still the compound is attached with metallic surface and their hydrogen will be there. So what happens, one hydrogen is added, the other hydrogen also added, CHO. This is how it happens. So once the saturated compound is formed, the compound will get away from the metallic surface. That's how it happens. So the very first example is reduction of alkene. Here I have written an example, and the catalyst used it is PtO2. Actually this PtO2 is called Adams catalyst, and it's not the PtO2, it's the Pt. When that is there in the reaction mixture, PtO2 will get the reduced to give platinum. That platinum is acting in the role of catalyst. I have a question over here, in an in-class question. The question is whether the given reaction is stereoselective or stereospecific. What is your opinion? You have to write down the answer. So when I have used the term stereo, I should even mention what is the stereochemistry relay of this compound. So whenever the catalytic hydrogenation happens, the supply of hydrogen will happen from the same side. So it's almost, we can say that from the same plane, the addition of the hydrogen happens to the alkene from the same plane. We used to call it as syn addition. That is what the mode of the addition. So you have to keep this point in mind. So remember, you have to answer to this question, and so whichever be the in-class question I am giving, you have to answer that, write down in a paper and upload in the Google Classroom. So please go through Clayton's textbook, and also I have given notes in detail about the catalytic hydrogenation. And you need to answer to this question also. Here you can understand that in presence of nickel catalyst, hydrogenation happens at 50 degrees Celsius and 100 atmospheric pressure, and the reduction happens for double bond, aromatic double bond, which is involved in aromaticity. So that also can happen, but it will never touch the carboxylic acid or ester or the aldehyde or ketone. And another point, it is very important, is the conversion of alkynes to alkene. Here the catalyst what we are using is called Lindlar's catalyst. And this Lindlar's catalyst, what is this Lindlar's catalyst if you ask? It is palladium in presence of calcium carbonate and intentionally or deliberately poisoned by using lead. It can be even written like this: palladium in presence of barium sulfate and quinoline. This combination is what we call Lindlar's catalyst. In this case also, in this case means in this palladium calcium carbonate poisoned with lead, there also if you use quinoline, the activity has been found to be increased. So this is what Lindlar's catalyst. And Lindlar's catalyst is having one of the very important aspect, that is the stereochemistry. So as I have told, the catalytic hydrogenation happens in always in the syn mode. So when you take an alkyne and treat it with palladium in presence of calcium carbonate, and it is poisoned with a little of lead. So what happens? You get an alkene, and which will have a configuration that is equivalent to cis. And please understand, previously we have seen alkene is getting hydrogenated to alkane. Here that further reduction will not happen. The reduction will be stopped over here, because we have intentionally added some poisoning agent. That poisoning agent will see that further supply of hydrogen will be stopped, so that further reduction from alkene to alkane will never happen. So not the point. Alkyne could be converted to alkene, not alkane, by using Lindlar's catalyst. Lindlar's catalyst is palladium in presence of calcium carbonate and deliberately poisoned with lead. It could be even in the support of barium sulfate, and if you add quinoline, the activity increases. Here we have got a interesting reaction, that is, we have already discussed carbonyl group. Carbonyl group will not be affected by this catalytic hydrogenation, but there is a particular reaction. There what happens is, in COCl, this Cl bond will be removed in presence of this Lindlar's catalyst, that hydrogen palladium in presence of barium sulfate. And what happens is, the aromatic ring will not be touched at this particular condition, and the COCl will get converted to COH, and it has got a name, you have learned it, is what we call Rosenmund reaction. Rosenmund reaction is for acid chlorides. Here you have a question, that is, what do you mean by Rani nickel? And the next is the reduction of nitro group. Catalytic hydrogenation could lead to the in presence of hydrogen. It could be platinum or palladium in presence of an agent, that is ethanol and acetic acid. The reaction happens to give amine. So what happens? Usually with 100% yield, that's what important. So nitro group could be converted to amine. So this is again very important reaction. By catalytic hydrogenation, nitro group could be converted to amine. So here also I have a question. The question is, how many electrons are involved in this reduction reaction? How many electrons are involved in this reduction reaction? So initially in the first class we were discussing about a reaction like this, and we have written 3-4 steps. In one step, if you keenly observe, you could see that there are two phenyl groups. There are two phenyl groups, and these two phenyl groups disappeared, and the reagent what we have used is the reagent for catalytic hydrogenation. So during the course of reaction, two benzyl groups disappeared during hydrogenation, and this process is what we call hydrogenolysis. Then what is hydrogenolysis, if you ask? What happens during hydrogenolysis, if you ask? That's a reaction which is liable to occur under catalytic hydrogenation. The reaction is nothing but the disappearance of benzylic group. Whenever a heteroatom, that in particular that is oxygen or nitrogen, is bonded to a carbon atom adjacent to the benzene ring. When it is bonded to a carbon atom adjacent to the benzene ring, we can say that oxygen or nitrogen is connected to a benzylic group. So when a benzylic group is connected to oxygen, it is called alcohol or ethers, or it is an amine, benzyl amine, benzyl alcohol, benzyl ether, or benzyl amine. If it is treated with catalytic, some catalytic hydrogenation agent, what will happen? The benzylic group disappears. This process is what we call hydrogenolysis. So see that whenever there is a benzylic group, or it could be told that whenever a heteroatom finds itself bonded to the carbon atom adjacent to the benzene ring. So this is the carbon atom, here the oxygen is attached, and this carbon atom is adjacent to benzene ring. So that's what we call it as benzylic group. It is attached to directly to the oxygen atom. If it goes for catalytic hydrogenation in presence of palladium catalyst, then what happens is this bond will be broken. This bond will be broken. Doesn't make any difference. this bond will be broken, or this bond. So what happens? The benzylic group disappears. This is what we call hydrogenolysis. Next reduction is Birch reduction. So when you talk about Birch reduction, it is the striking term. It is dissolving metal reduction. Dissolving metal reduction. So you must how do you prepare sodium ethoxide? How do you prepare sodamide? If you ask, so the sodium ethoxide is prepared when you dissolve sodium into ETOH. So what happens is the sodium will get oxidized to sodium Na plus and electron, whereas this ETOH will get ionized to give ETO minus plus H plus. ETO minus and H plus. And this electron will go with this hydrogen to give 2H plus plus 2 electron gives H2, and they will fly away. That's how. So reduction of hydrogen happens. And most surprisingly, the same thing happens when you take ammonia in presence of ammonia in presence of this alkali metals or alkaline earth metal. So here what happens is the Na plus and this electron will get ammoniated. That's how it is told. NH3N. Electron will be written like this. ENH3N. This is what we call ammoniated electron. And if the solution is allowed for some more time, this when the ammoniated electrons are present, the color of the solution will be blue. So if you keep the solution for some more time, what happens is this electron will be absorbed by this NH3. NH3 will give NH2 minus plus H plus, and this H plus will get reduced to give hydrogen. So Birch, that was his name, he was thinking, he has given a thought. What is that is, if the solution could be provided with some substance which is ready to accept this ammoniated electron better than this proton, then what will happen? That's how it led to Birch reduction. So you could see one of the example of this Birch reduction. Here the benzene is getting reduced to give cyclohexadiene in presence of lithium with ammonia and in presence of ethanol. So the surprising point over here is the aromatic ring has got reduced, and not only that, the product is having unconjugated diene. How does it happens? The product you got unconjugated diene. So the answer to this question will be given by the mechanism. Birch found that benzene is a better substance to accept this electron, ammoniated electron, than H plus ion. Why benzene is a better substance? It has got lowest lying anti-bonding orbital, that is benzene's lowest unoccupied molecular orbital. You must have learned it in molecular orbital theory treatment in the other class. And the species we get can be represented in several ways. That is actually called radical anion. It has got an anion as well as a radical. And this radical anion is highly basic. When it is highly basic, what will happen? One of the proton from this ethanol will be absorbed by this radical anion, and there will be the formation of a just radical. A radical will be produced, and this radical will cannot be stayed as it is because it is a very reactive species. It will be accepting one more electron from the solution in order to give an anion, and this anion interestingly can have resonance. So I have written two important resonance structures over here. See, these two are the resonance structures, and it will lead to the product. So this is how it goes, and you will get a product. This is what the product, and it is, again you may have a doubt. Sir, you will ask, sir, there is conjugated diene and unconjugated diene. Why the product is going for the unconjugated diene formation? So answer to that question is, beyond resonance there is a factor, that is the orbital interaction. So here the central carbon, the hydrogen ion will be attached to the carbon atom, which is at the central. I mean, either it is at the center, that's how it could be told. The hydrogen will be attached to that carbon only, means so that it will favor the formation of unconjugated diene, not conjugated diene, as a result of orbital interaction. Again, it is related to MOT, symmetry, all interactions, and not the stability that is provided by this conjugated diene. So you have a question over here, next in-text question. I have taken a substance that is benzoic acid, and I have taken anisole. So we were discussing about the resonance, and this anisole, what type of impact will be made on a benzene ring, and this carboxylic acid, what type of impact will be made on benzene ring, we already knows that. So the question is, what will be the product for this particular reactions, and you need to explain it on the basis of mechanism. And I remember this question was repeated 2 or 3 times in the university exam. So this is about Birch reduction. So you have to answer to this question too. So we were discussing about Lindlar's catalyst, and the speciality is Lindlar's catalyst will give cis product as the alkene. Here the Birch reduction of alkynes will give alkene. It is not cis, it is a trans product. That's what the difference. So you are getting a trans product, and the mechanism for this reaction follows the same what we have seen for aromatic rings, and the only difference is the anion free radical is, it is strong base enough to absorb or take away a proton from ammonia, so that the amide will be formed. And you don't have to add, just like in the aromatic Birch reduction of aromatic substance, you need to add ethanol as the substance which donate proton to the substance which is getting reduced. Whereas here in the Birch reduction of alkynes, you don't have to add any particular reagent that will source out a proton. So ammonia itself is enough. So what happens is the anion radical is strong enough as a base in order to absorb a proton from ammonia. So what happens is a vinyl anion is getting produced, and this vinyl anions are geometrically unstable and always choose to be E configuration. E configuration means it is equivalent to trans configuration, and if you look at the product, these two are the hydrogen atom, it is getting added and it will be on the opposite side. That's why Birch reduction promotes only trans alkene products. So hope you are understanding all this. So please upload the in-class questions to the classroom.